Okay, so last class we were talking about this problem of the best fit subspace. So we defined what it is. We are given some data set and we would like to find the best sort of low dimensional space that approximates the subspace. And we also introduced this notion of right singular values, which were giving us a handle on how to solve this problem. And today what we're going to do is study another seemingly unrelated problem called low rank approximation. But as we will see, it's kind of this other side of the same coin as the best fit subspace problem. And finally, this will lead us to the notion of singular value decomposition, which is very important in numerical linear algebra, data mining, and sort of pre-processing data. And we'll see how that helps us solve both of these problems in one go. Okay, so just to recall what we were doing from last time, we defined the problem as follows. So we're given some data set X. We write it as a matrix where the rows are the elements of the examples. And given any subspace S, we are looking to minimize the error defined as the difference between the point and the projection to the subspace, or maximize the correlation with the subspace, which measures how much of each vector is contained within the subspace, right? And we defined the goal for this problem of best fit subspace is either to minimize the error or equivalently to maximize the correlation. This was something that we showed. Finally, we also defined this notion of first right singular vector, find a vector V which maximizes the inner product with our matrix X. And we also define the second right singular vector as the same maximization problem with the additional constraint that you have to be perpendicular to the previous one. And we define these things iteratively. And the non-trivial thing that I claimed last time was that the span of this first k right singular vectors, which we define here, actually gives you a solution to the best fit subspace problem whenever the dimension you're looking for is k. We showed this for k equals 2, but you can actually show it more generally, and I'll leave that as an exercise for you. So k equals 2, we did in class, general k is similar. Okay? So far we have kind of a handle on best fit subspace through this problem of finding singular vectors. But this still doesn't say how to find these right singular vectors, right? So first we need to tell you we need to figure out how to find even a singular vector, and then figure out how to find the subsequent singular vectors. We'll address all of these questions in one shot via a completely different problem. Okay? So let me now talk about this other question that I'll call low rank approximation. So put your thoughts on the best fit subspace problem on hold for now. We're switching tracks and then we'll come back to the question in a few minutes. Okay, so what's the low rank approximation problem? The question is the following. So you're given some matrix X. Okay, it's some big n by d matrix. Now think of it as a huge matrix. Okay? And your goal is to approximate this matrix in some way. So approximate X in some simpler way. Okay, so we think X is some complicated thing, but there's a simpler structure underlying it, and our goal is to find the simpler structure. So first of all, we need to sort of formalize this rigorously, right? So often one of the first steps is, we have some intuition for kind of the general principle that we're looking for, which is, okay, I want to find a simpler approximation for my matrix, which looks kind of very messy, but then we have to formalize it mathematically, right? So here there are two questions to ask. First is, what does simple mean? Right, I'd like to know what does simple mean, really. And the second question is, what does approximate mean? Okay, so we are approximating a matrix which is n by d matrix, which has n rows and d columns. I want to approximate it in simpler way. So let's tackle each of these sort of essay questions, right? So what does simple mean? What would be a simpler matrix that you can look for? Any suggestions? Like among all matrices, what matrices are simpler in some intuitive or statistical sense?
Maybe a simpler matrix would have a larger null space.
Larger null space or equivalently low rank. Okay. So rank of the matrix is the number of linearly independent columns, or the dimension of the span of the columns, span of the rows, and all kinds of goodies like that, right? So rank of a matrix, there are many different ways to define it. Is dimension, span of columns space, which is also equal to dimension, span of rows. Right, so asking for a smaller null space equivalent to asking for a larger null space equivalent to asking for a smaller rank. All right. Okay. So you might ask, so for example, right, here's a matrix it's an n by d matrix, and so let's say the matrix has some vector, v, some column vector, let me use u, that is being repeated again and again. It's intuitively a simple matrix, and what is the rank of this matrix? Just 1, right? So the rank of this matrix is only 1. And why study rank as a notion of simplicity? Any guesses? I mean, it makes intuitive sense that, a matrix is simple if it has small rank, but there are very concrete and important reasons why that is true. From a computational perspective, can you tell me one reason why rank would be a nice notion of simplicity? Okay, so let me state it this way, right? If rank of a matrix is R, then I can write the matrix, right? So this is kind of, think of it as a tall and sort of big matrix, right? But I can write it as, hold on. Okay, so a matrix is of rank R only if I can write it as a product of two matrices. Okay, an n by d matrix is of rank R if and only if I can write it as a product of two matrices where each of which has dimensions n by R and R by d. This is kind of a simpler way to represent or break up the original matrix as a product of two things. Now, from this representation, one great thing here is how many bits you need to even represent the matrix. Right? So one advantage is compression. If I were to store the matrix X as is, how many numbers do I need to store? I need to store n times d numbers to store X as is. Right? But to store u and v from which I can reconstruct X, how many numbers do I need? N times r plus r times d numbers to store u comma. Okay, so this is something like n plus d times r. So you're going from something n times d to n plus d times r. So imagine you have a million by million matrix which is a rank 20. Then to write down the original matrix, you would need, almost like, think several, like tens of GB to write it down, to store the matrix as is. But if it were actually a low rank matrix, I can store it as u comma v, and then it would take an order of magnitude less memory to store it. So that's one advantage from a computational perspective. The second advantage, which is not something that we're going into, is that there are many probabilistic / statistical models that yield low rank matrices. So often, there are many important models, something like latent semantic indexing and things like that, where the underlying model you have for how the data was generated would tell you that you must have started with a low rank matrix and then added some noise or things like that. So in that sense, low rank, or trying to find a low rank representation of our original matrix, is a very nice thing to shoot for, both in terms of computational advantages, one facet of which is just storage, the other facet is like the statistical properties. And as you'll see, even in terms of time complexity, a low rank is very advantageous. Okay? That's the answer to the first question of what does simple mean. But how do we quantify approximation? Any suggestions for that? So now I decided that, okay, my notion of simplicity is low rank. So you give me your matrix and I want to find a low rank approximation to that matrix. But what is the notion of approximation that you'd want? Any suggestions? So one of the most natural things is, of course, to look for the squared error, right? Just like in square linear regression and in everything else that we've been doing, we can look at the squared error, right? So we have our matrix X, okay? And I'm trying to approximate it with something which is low rank, right? So this is my X, I want to approximate it with some X tilde which has low rank. Okay? And a natural notion to look for is to just look at the sum of squares of the difference of the entries. For each entry, check how far the entries are. For each position, check how far the entries are. Right? So that's how we'll quantify approximation. Okay, so let me actually define it properly. So the sum of squares of a matrix has a name for it. just as the Euclidean norm is sum of squares of the entries, there's a name for matrices. So for any matrix A, the Frobenius norm of the matrix is defined as you look at the sum of squares of the entries to the power half. It's like the length of the vector, except that you're just applying it to matrices. Okay. And for approximation, what we can look for is, which is just sum of squares of the differences. Okay. So we'll try and find a low rank matrix which minimizes the sum of squares of the differences between x and x tilde. Alright. So with this, we are now ready to state our low rank approximation problem. So what is it? So given x, which is some n by d matrix, and k, which is our desired rank, this is our input. The output is, something that minimizes the rank, minimizes the squared error or the Frobenius norm squared error, subject to rank of x tilde being at most k. Okay, so that's a very important problem in data mining, which is given your data set, I want to just find a low rank approximation to the whole matrix. Any questions about the formulation? So just as a heads up though, we are only studying this for Frobenius norm, but there are many interesting norms that you can ask this question for. For some norms we can actually solve it, some norms it turns out to be some other notions of error, how you quantify approximation, the problem is NP hard and so on. Okay? And in this lectures, we'll study the Frobenius norm, and I'll give you a hint towards solving another very important case, which is a spectral norm. But this is not something that we've defined or studied, so I'm not doing that here, but that's very important in practice as well. Okay, so that's our question, but let me describe one concrete application of this problem to a really real-world challenge. Okay, so how many of you have heard of the Netflix challenge? Okay, I see a few people. So basically this was something that came out, I think, just as I was entering grad school, eons ago. So it was all the rage when I just entered grad school. So of course, every one of you has heard Netflix, and maybe some of you are already watching it right now, but Netflix did this kind of curious experiment, but it was quite influential in how data mining took this challenge and developed this method. Right? They said, okay, so we are releasing this data set, which is of users, 500k users, and they picked some 17k movies. Okay. And for each of these users, they kind of gave out some ratings. Not every user rated all 17k movies, but they kind of picked the 17k sort of movies which have the most number of ratings, and they filled them out. They said, okay, this user rated this movie as a 1, star means we don't know, and this is like a 2, maybe this is a 5, and so on and so forth. Okay. So from the set of all ratings that they had, they released a subset of those ratings. Okay, not everything that was rated was released to us. And the total number of entries here is approximately 100 million. So it's a huge data set. Back in the day, especially with the hardware that long ago, maybe around 15 years ago, you couldn't even fit this data set in your RAM that easily. You had to do a lot of hacks to even do that, right? And they released about 1% of the entries. So approximately 1 million entries. Okay. And then they said, okay, they set up like a server where you can submit your submissions. Your submission basically is some way to fill out these missing entries. So the goal was guess missing entries. Okay. And guess missing entries basically to minimize the squared loss. If it was 5 and you guess 4, then you got a penalty of 1. Whereas if you guess it was 1, then you got a penalty of 16. Things like that. Okay? With small squared error scale appropriately. The scaling is kind of natural, right? And the challenge was, they said, we have some baseline algorithm. They had some algorithm that they were using to give predictions to users, to recommend movies to users that they were actually using, not just like, it was not just a theoretical algorithm, that's what was running on their machines. And they said the first team to beat the error that we were getting by 10% will get $1 million. Okay, so first team to do 10% better than baseline gets. Okay. And you can imagine, this was a big incentive. People started forming all kinds of collaborative teams to attack it and so on. But it's kind of so silly that, they would put such a big price tag and they didn't even take a course like what we're doing now. So what do I mean by that? So if you see such a thing like that, the standard thing that people used to do in data mining is something like this. Step 1, you pre-process the data. Okay, meaning you just sort of center the data, normalize the entries and things like that. Okay, so this is something that we are not covering in this course so far. But often things have to be like numbers which are negative and positive for many of the things that we are doing to make sense. So here, if the numbers are all positive from 1 through 5, you shouldn't run the standard algorithms here. You would like to sort of center them so that the mean is 0, normalize so that things are kind of in some range, and then do whatever we do. So given what we are discussing, what would be a way to try and approach this question? Let's say you are actually studying low rank approximation. What would be the first thing you try? Any guesses? So there are lots of missing entries, right? So if, let's say I center the data so that, okay, maybe even forget center it, right? What would be the first guess for these missing entries for each user? If you didn't know anything about the movies, what would you guess it?
Just the mean rating.
The mean rating, right? If I'm giving 5 to all the movies there are, including all the junk ones, presumably I'm going to rate 5 to all the other missing ones too. Right? Whereas on the other hand, like a harsh critic who only gives 1 rating to any movie, including some of my favorites or whatever, then I might just as well give 1 for the missing entries, right? And the flip side of that is when you centered the data, you made the mean 0, right? You moved the things around so that you basically subtracted the mean. So what would you do for guessing the missing entries? Right, so put 0 for the missing entries to get matrix X. Okay, so the original thing was not a full matrix, right? There were a lot of missing entries. But now I actually have a matrix which has all the entries filled out. Many of them are 0. But now, 0 is not a good guess. The mean is not always a good guess for all of the remaining movies, right? You want to use some other information about filling these entries. So what would be the next step? How can I refine this X to potentially get a better approximation to the missing entries? So let me give you a hint. Imagine that for some whatever reason, the unknown matrix with all the entries filled in, the true ratings matrix, is low rank. What would you do in that case to guess the missing entries? What would be a good way to approach that? Well, find the best lower rank approximation X tilde to X. For some K, step 4, predict using X tilde. Okay, so that's it. That's a very, we just defined low rank approximation. So we figured out all the missing entries with the mean, but instead of just using the mean, we are going one step ahead, finding the best low rank approximation for some K that we'll pick, right? And then use the resulting matrix X tilde to guess the missing entries.
Do we have to know, or do we have to assume anything about like the way the data is missing before we can go around?
Yeah, that's a good question. You could, if you want to theoretically analyze it, there are many ways of, sort of formulating it so that you can understand how the missing entries are generated. And that's a very good question actually, because sometimes, the way you penalize the errors in this problem, you'd like to take into account the frequency with which each user is rating movies. Okay, like, if I only rate 10 movies, somehow maybe you have less signal from me. So for that row, you'd like to reduce the weight and things like that. But as a first step, let's assume that the samples were kind of random, uniformly random. Just for, the first step. If I was at Netflix, this would be, and they took any course, let's say on machine learning, especially this one, then they would have done this. Okay? Predict using X tilde. And what people realize immediately is that if you run this with K, which is like 30, okay, then you bet the baseline by 3.5%. Right? So remember, the challenge was, okay, beat us by 10% and you got $1 million. Unfortunately, it wasn't a sliding scale because this was giving you 3.5% boost on the baseline. So I don't know why they didn't do this, but that's what happened. And in fact, it's not just sort of to get 3.5%. what people eventually did to beat the 10% kind of builds on this sort of low rank approximation approach. Right? So you try and find more complicated but sort of succinct representations of the missing entries. Right? So low rank means U times V, right? Where U has only R elements in each row. So instead of combining them just by inner product, people try to combine by all kinds of fancier models, but it was still something like U times V. And that's what eventually led to beating the challenge. Took some time. I think it was around maybe 1 or 2 years before people eventually did beat the challenge. Okay. So that's kind of a example of how people might use just this simple low rank approximation in the real world. And it's often the first step that you would do in handling matrix valued or high dimensional data. Just as I said, principal component analysis is one way to sort of pre-process the data, kind of rule out some errors. Low rank approximation is also done for matrices. Any questions about this? So that's an application of the problem, right? Now let's see how can we even solve this question. So just as with the best fit subspace problem, we were optimizing over subspaces there, which is like a very complicated thing to think about when you are optimizing on. And here we're kind of doing the next step, which is optimizing on low rank matrices, right? How do I even parameterize over the space of low rank matrices and then try and minimize the least squared error, right? It seems pretty complicated again. Fortunately, no one needed to do this step 3, right? So there was this magical step 3 here which said, okay, find the best low rank approximation, right? But step 3 was basically solved around 200 to 300 years ago by very different fields. Many different people discovered it, and it's one of the basic tools in numerical linear algebra. So this leaves us, almost as an excuse for studying this fact about matrices, which I'll call singular value decomposition or SVD. Right? So you can teach a whole course just on studying SVD and its implications, but that's not what we're going to do. I'm just going to state what are its properties and some magical, facts about it that we will use to solve the low rank matrix approximation, and then also the best fit subspace problem. Okay, so let's take a 5-minute break, and when we come back at 10:40, we'll start discussing singular value decomposition and how it relates to computing the best low rank approximation. Okay, all right, let's resume at 10:40. So, all right, welcome back. So I forgot to announce at the beginning of the lecture, but assignment 3 will be out today, and it is due next Monday at 10 p.m. as usual. And it will cover the content of lectures 9, 10, 11, and 12, which is going to be on Wednesday. Okay, so keep that in mind. And as usual, it will also be up on the course website. So look there for the assignment. Okay, so singular value decomposition says something about any matrix. It's a way to factor or write a matrix as a product of other matrices which have some nice properties that we can exploit. So in particular, given any matrix X, no conditions on it, we can write it as a product of 3 matrices U, sigma, V transpose. So the third matrix we are writing as transpose, meaning the actual V would be a D by R matrix. Okay, where R is going to be the rank of the matrix X, and it's supposed to satisfy all of these properties. The first property is that the columns of U are orthonormal, meaning they are all unit norm and orthogonal to each other. So columns of U are orthonormal. In other words, if you actually write it out, U transpose U would be the identity matrix in R dimensions. So if I look at U transpose U, which is like this wide matrix times its transpose, then I'll get the R by R identity matrix. And the next condition is the same for V. See, columns of V are orthonormal. So it's a very special representation. It's saying I can factor it as product of three matrices, where the left and right have this sort of columns being orthonormal. And not just that, the middle one is also very special. The middle matrix sigma is a diagonal matrix. So all of its off-diagonal entries are 0. And finally, and this is very important, is that sigma has non-negative entries. Okay, so it's a diagonal matrix which has only positive numbers on the diagonal. So it's 0 here and positive entries on the diagonal. And this comes from numerical linear algebra. Okay, let's not do that. Okay, so any matrix can be written as a product of three matrices, each of which satisfies these seemingly very stringent conditions. And just as a remark though, some texts take sigma U comma V to be d by d with some zeros. So if you've seen singular value decomposition before, in some places it's written as a case where sigma is a bigger matrix, it's a d by d matrix even, which has zeros in the some entries. But let's just stick to this R by R formulation where we'll think of R as the rank of the matrix. Okay? Let's do some examples to get a sense of this definition. So let's say I have a diagonal matrix with positive entries. So imagine my matrix was actually a square matrix, and it had, let's say 1, 2, 0.1, 0.3 diagonal. So what would be a singular value decomposition here? Any guesses? So I need U sigma V where they satisfy those conditions, right? So what would be one way to factor it in that way? Well, I just need to find some factorization which satisfies those conditions, right? And I'm claiming here's one, pretty straightforward one, which is I can take the first matrix U to be the identity. Right? All of its columns are actually orthonormal. And I can take this one also as the identity. Oops. But what should I take the middle one? The only constraint on the middle one, sigma, was that it should be diagonal and have positive entries. So what can I do then? I can just take this to be x. Okay? So this is a singular value decomposition of the matrix. I'm writing it as a product of three matrices where each one satisfies the conditions required of the singular value decomposition. Okay? Now, how about the case where I have a diagonal matrix, once again, with just a diagonal matrix, meaning I might have some negative entries. So let's take a concrete example, right? So let's say maybe the matrix I'm looking at is 1, 0, 0, minus 1. Okay, so this is my x. How can I get a singular value decomposition for that? Any guesses? I can't do the same thing that I did before, because if I use x as sigma, then it won't have, sigma has to have positive or non-negative entries. And that wouldn't satisfy the condition. So what can I do to fix that? Any suggestions?
Could you change the sign of either the U or B matrix?
Exactly, right? So let's do that. So I can try the same thing. Actually, let me make it minus 2 just to be clear. What I can do is take this to be 0. Just flip one sign here and this. Okay. So I flip the sign of one of the entries in the identity here, and then I could flip the sign in sigma to make the entries positive. And you can check that this satisfies the equation, and all the conditions on U sigma V are satisfied. U has orthonormal columns, V transpose V has orthonormal columns, and sigma has non-negative entries and is diagonal. Okay? Let's do one more example, maybe a couple more examples just to understand this better. Suppose I actually have an orthonormal matrix. I give you a matrix whose columns are already orthogonal to each other. What would be an SVD for that matrix? Right, so it's an n by d matrix, but the columns are orthogonal, are orthonormal. So what would be an SVD from this matrix? Again, remember that all we need to do is to come up with this U sigma V which satisfy these conditions, right? So I can take a suggestion in the chat, I can take U to be x, and sigma to be square identity, and V also to be identity. Okay, so this is x, identity, identity. And you can see that all conditions are satisfied just by definition. We know the columns of x are orthonormal, and I have the product equals that. Okay? These are examples just to give you some sense of what they are doing. And if you know eigenvalue decomposition, let me say that the main difference between eigenvalue decomposition and singular value decomposition is that when you do eigenvalue decomposition, the entries in the middle diagonal matrix need not be non-negative. Right? They're not required to be non-negative. They could be negative. Okay? Whereas in singular value decomposition, we require the entries in the middle matrix to be non-negative. Okay? So that's the main thing to keep in mind. So, okay, all that is good, that's good numerical linear algebra to know. But why is SVD useful for us? Okay, so why study SVD? And the reason SVD is useful for us is the following two magical properties that I'm not going to prove. They're not maybe too difficult, but they do require some work. Two magical properties of SVD. Okay. So let me say that the first thing we'll do is, suppose I have my x, I write it as I take a singular value decomposition. Okay, so I'm taking the singular value decomposition here. X is U sigma V transpose. Okay, but let me assume that I write this sigma where in decreasing order. Okay, so I'm ordering the singular values so that they're increasing as I go down the diagonal. That's one thing I'm doing. And the other thing I'm going to do is to call the rows of this V transpose, V1 transpose, V2 transpose up to VR transpose. Okay, so I'm ordering the sigmas in this way, and the columns of U I'm going to call U1, U2 up to UR. Okay, so far all of this is pretty simple. Now, the two magical properties are that singular value decomposition solves both of our problems. It solves the best fit subspace problem and the best low rank approximation problem. So what do I mean by that? If you see here, I call them V1 through VR for a reason, which is that Vi is the ith right singular vector of x. Now this is a magical property because we define singular vectors in a completely different way. We said, okay, the first singular vector is the solution to some maximization problem. Maximize x times v, the norm of the x times v, where v was unit norm. But here I'm saying if you compute the singular value decomposition and order the middle matrix sigma in terms of decreasing entries, the first row gives you the solution to the right singular vector optimization problem. Okay, so recall so this was something like argmax, the first singular vector we defined as argmax x times v, where v was unit norm. And it's saying the first row of the singular value decomposition, when I order the singular values in decreasing order, gives you the solution. Okay? And the second magical property is that for any k, if I want the best rank k approximation, all I need to do is to ignore all but the first k non-zero entries in sigma. Okay, so what do I mean? Xk equals so I take only the first k columns of u and the first k entries of sigma and the first k rows of the rightmost matrix. Let me call this matrix xk. K is 1, I'm just taking the first column, the first entry, and the first row. K is 2, I'm kind of stripping out all but the first two things in each matrix. Right? Is a solution to best rank K approximation. Okay, and this is called the Eckart-Young-Mirsky theorem. And this is from 1936. Okay, so people already knew how to solve the best rank K approximation in terms of the singular value decomposition that we've been discovering. Does this make sense? So remember, here you have zeros, and the first k entries gives you the best rank K approximation. Any questions about this? So if I can compute the singular value decomposition or the SVD, I solve both problems in one go. The best fit subspace and the best low rank approximation. Because I can get the best fit subspace by looking at the span of the columns of V, and then looking at the k entries gives me the best rank solution. So these are the two magical properties of SVD which make it so useful in numerical analysis. Okay? So this kind of solves the problem, but we just kind of, it seems like we pushed the problem down the line, right? We just punted the problem away and said, okay, if you can compute the SVD, then I can solve both problems. But how do I compute the SVD? I mean, even its existence seems kind of bizarre, right? Why should there always exist such a factorization of any matrix? Okay? We'll address those things in a little bit. But before going there, we have to build up some infrastructure to compute the best, to compute the SVD. All right. So basically, summary. Knowing SVD solves both problems. But how to get SVD? Okay, so we'll address that next. How do I compute the singular value decomposition? And the reason we're taking this route is that once we use properties of this decomposition, the algorithm kind of, is easier to arrive and to figure out when it will work and when it won't work. So let's look at some properties of SVD that we need to use to get the algorithm. So some more properties of SV. Okay, so these are just from, we have the 4 things from the definition, right? That the columns of U and V are orthogonal, sigma is a diagonal matrix and has non-negative entries. Let's look at some implications of those. Okay, so the first one is that suppose I tell you, I'm not going to draw the picture again, but X is U sigma V transpose is an SV. The entries of sigma, we write them as in this decreasing order, and these are called the singular values. Just as we defined singular vectors, the entries of this middle matrix sigma are called singular values, just numbers. So this is called the first singular value. This is the second singular value, and so on. Okay? So the first thing is, I can also write down X is this U sigma V transpose. So remember we had, okay, let me try it one last time. Okay, so I'm writing the big matrix as a product of these things. Okay, and because the middle matrix sigma is a diagonal matrix, it gives you an alternate and presumably simpler way to write down this matrix. So let me actually use a different letter here. Okay, so if the columns are U1 up to UR and the rows here are V1, V2, so on as before, then I can write down this matrix as a sum of these other matrices. And the nice thing here is that each of these is just an outer product of 2 vectors. It's rank 1. Right, so we're just saying, okay, there is a number here, which is just a number, and then I just have a single vector. Okay, so I'm writing it as sum of these outer products of individual vectors. It's equivalent to this. The second property that we'll use is a relation between the U's and V's. Okay, so for some reason, let's say I gave you only sigma and V, you can infer U, and alternately, if I give you sigma and U, you can infer V. And in fact, given U or V, you can even get out sigma from it. So let's see how. So my claim is that X times Vi is actually, so let's use little sigma L for these diagonal entries. So if I multiply X with V, I get a scaling of U. Okay, so if you know the definition of eigenvalues, this should remind you a little bit of it. That in eigenvalues, you're looking for X times V equals lambda times V, But here it's kind of v's become u's, but it's the same v and u for every L. So why is this true? So let's use this representation, right? So we have UL times VL transpose. That is X, I'm multiplying with VL. So I can expand this as, you know what, actually let me use I. I think that makes more sense. Okay. Now, what can you tell me about these inner products, VL transpose and VI? What are those numbers? So remember, the property of V is that the columns are orthonormal. So the different V's are orthogonal to each other. Okay. So everything except the index where L equals I will give you 0. Right. So this is just saying what I have here is summation L equals 1 through R sigma L of VL comma VI times UL. Okay, and we know that these are 0 except when L equals I, because the columns are orthonormal. So I just get sigma I times UI. Okay, this is 0 if L not equal to I, 1 if L equals I. And similarly, you can check that basically X transpose times UI equals sigma I times VI. Like you flip and you get the same equation. And the other thing that we'll need is sigma I. So here, if I take the norm of this vector, what do I get? The length of the vector x times vi is exactly sigma I, because ui was a unit norm vector. So when I take the norm, I just get this. So in particular, this implies that ui is x times vi divided by norm of x times vi. Okay, what this is essentially saying is that if I give you just the right singular vectors, I can compute the singular values and then I can compute u's. Oh, and forgot to say that u's are called the left singular vectors. Okay, so u's are called the left singular vectors, sigma are the singular values, v is the right singular vectors. And if I give you the right singular vectors, you can compute the other things just by using these two equations. Okay. So even though it seemed like, to compute singular value decomposition, I had to compute u, sigma, v. All I need to do really is to somehow compute one of them, not one of them, but I need to compute v or u, and I can infer the others. Okay. So these will help a little bit in computing the SVD, but the real claim and the main property that makes singular value decomposition so useful for computation and even feasible to compute is the following. And this is something that we sort of touched on when we discussed the greedy approach to computing singular values. Right? Remember in last class we said, okay, I can compute the first singular vector, and then we define the second singular vector based on the first singular vector. Okay, we can actually make it into an algorithm as follows. So V2, or we say second right singular vector, SV is short for singular vector, of X is equivalent to the first right singular vector of okay. So if I know the first singular vector u1 v1 of X, then to compute the second singular vector, I can once again compute the first singular vector of a different matrix, of the matrix X minus sigma 1 times u1 v1 transpose. So imagine someone gave you a black box, like a library call to compute the first singular vectors u1 v1 and sigma 1. Then I can iterate it to get the remaining singular vectors. Okay, so let's quickly see a proof of this. It's really sort of almost true by definition, I'd say. So X minus sigma 1 u1 v1 transpose is equal to right. This was our definition. If I wrote down X exactly as sum of these outer products, right? So I push the first term to the left hand side, so I just get the sum of the remaining from 2 to R. So that means I'm writing this matrix as right. So these outer products I can again put together as U2 up to UR, and I have sigma 2, sigma 3, sigma R, 0, 0, and then here I get V2 transpose, V3 transpose, so on, VR transpose. Okay. So X minus sigma 1 u1 v1 transpose is exactly this guy. So this is a singular value decomposition of this subtracted matrix, right? So basically taking out this one term gives me the singular value decomposition of the remaining things, just because I have this equality. And the columns of U are orthogonal, so these are orthonormal. The rows are orthonormal, so those are orthonormal. And sigma has non-negative entries. And they are in decreasing order. Sigma 2, sigma 3 are all decreasing order. Okay? So, by magical property 1 or MP1, first singular vector or first right singular vector of X minus sigma 1 u1 u1 transpose is V2, right, which is exactly what we wanted to say. The first right singular vector is the second singular vector of X. Any questions about this? This is very important thing to understand, that you can peel off singular vectors one after the other. Compute one, subtract it out, compute another, and so on. Okay? We can actually generalize this to get the following. Plane Vi ith singular vector of x is the first singular vector of x minus sigma 1 u1 v1 transpose minus sigma 2 u2 v2 transpose minus so on. Okay. So what this means is that there is a greedy strategy to compute all the singular vectors. Corollary: if we can compute first singular vector, then we can compute right. So if I can compute the first right singular vector even, then I can compute sigma 1, then I can compute u1, then I can compute x minus sigma 1 u1 v1 transpose, and then I can iterate this process to compute all of the singular values and singular vectors. Okay? Any questions about this? So this is a greedy way of doing this computation where I compute the singular values one after the other. And just to kind of put this in context though, people in numerical linear algebra, like when you do MATLAB for instance, or NumPy and things like that, when you ask it to compute the singular value decomposition, it is not going to do one after the other. When I want all the singular values, it's not using this greedy approach. In fact, there is like a straight up approach based on matrix inversion and things like that. To compute the singular value, it can compute SVD directly in time O of n times t squared. Okay. So there is almost like a cubic algorithm to compute the singular value decomposition, full singular value decomposition. And this is what's implemented in most platforms, but there's one catch, right? So think of the metrics challenge, right? So there n was 500k, d is 17k. Then even to store this matrix, like if I wrote a dense matrix, this n times d is 8 GB in memory. So there's just there's no way I can use, compute SVD in MATLAB for this huge 500k by 17k matrix directly. Even to store this full SVD, if I ask you to store the full SVD, it would take me 8 GB of memory, which is just prohibitive. Okay? And the main thing we'll study is, what if I don't want to compute the full singular value decomposition? Maybe all I need is the top 20 singular vectors. Right? So I don't care about computing the full SVD where I write down x equals u sigma v transpose. But I want to compute just the top 20 singular vectors. Can I do that without having to compute the entire 17k by 17k singular vectors and so on? So question: what if I want only the top, let's say 20? Okay, and here's where greedy is very powerful. because I can circumvent this bottleneck of computing the full SVD and at least in principle feasibly compute just the top 20 by doing one after the other. I'll compute the first singular vector and then the next one and so on. Okay, so in the starting today and in the next lecture, what we're going to do is talk about another very important algorithm that's called the power iteration. And what it does is to compute first singular vector. Okay, and it will do it in time which is almost linear in the data size. To compute the full SVD, n times d squared is way too expensive, but here we'll run it in time which is basically the size of the data set, like n times d. Okay, and as we'll see, it can be very powerful in under more assumptions on the matrix. So it will give us computing the first singular vector, and as a remark, once we know to compute V1, we can compute sigma 1, we can compute U1, and then compute x minus sigma 1 U1 V1 transpose. Okay, so once I can compute this first right singular vector, just this one vector V1, if I have that ability, I can crank it up repeatedly to compute everything. Any questions about this? Okay, but how do I compute this first singular vector? Okay, so the idea of the algorithm. So today I'll just kind of try and sketch the intuition behind the algorithm, and hopefully you can prompt me towards the actual algorithm, right? It's fairly intuitive when you kind of, start with something which is non-trivial. So I suppose this is the singular value decomposition. Okay. Now this is equal to U sigma V transpose. So they are both representations of what X is. Okay. And so the idea is something to understand how singular value decomposition changes under matrix products. So what do I mean? Let's look at this matrix. I'll call it Y, which is X transpose X. Okay, so what is X transpose X? My claim is that when I look at this big matrix X transpose X, something very nice happens. So let's work through it. So I have to take the transpose of this guy. So I get V sigma U transpose. Right, this is X transpose. And X is U sigma V transpose. Does this simplify in any way? How does it simplify as? What can I use to simplify this matrix? Any suggestions? So let's look at what's happening here. I can move things around, so group the parentheses differently and write this as this guy. Now what is this middle matrix U transpose U? Let's go back to the definition of singular value decomposition, right? So by the definition of singular value decomposition, the rows of U were orthonormal. Sorry, the columns of U were orthonormal. Right? In particular, we said, if you go all the way back, the four properties of singular value decomposition were, the first one was the columns of U are orthonormal. So meaning U transpose U was just the identity matrix. Right? So as a result, what I get here is that, so I get V sigma times U transpose U times sigma V transpose, okay, which is actually just V sigma times identity times sigma times V transpose. Okay, so which is just V times sigma squared times V transpose. So somehow when I look at X transpose X, all the information about U disappears. There's no U, there's only V, right? It only depends on V and sigma. And what are the entries of sigma squared? Remember, sigma was a diagonal matrix. So what are the entries of sigma squared? Right, so I get, go ahead.
It's just the diagonal entry squared, right? Like
exactly. So I can write this as, I have my V, and I'm just going to get sigma 1 squared, sigma r squared, and then V transpose. Okay. All right, this seems somewhat interesting. Whatever, it's some algebra, right? So, but why are we doing this? Now, suppose I kind of went along with this and I asked you to compute y squared. So, what is y squared? It's going to be V sigma squared V transpose times V sigma squared V transpose. So, remember that Y is a D by D matrix. So I can ask for y squared, and this is what it is. Can you simplify this in any way? What do you think?
Do the same thing again?
Exactly, right? So what happens if you do the same thing again? We can group this V and V. And one of the defining properties of SVD is that the columns of V are orthonormal. So V transpose V is also identity. So what am I getting? V sigma to the 4 times V transpose. Okay, somewhat interesting. So what I have here now is basically like V hasn't changed, but the entries inside, instead of becoming squares, became to the power 4s. Now what happens if I look at y cubed? Any guesses? Just go ahead. I know it's obvious, but just guess, right? So I multiply it with, so let's use the same equation. I have V sigma to the 4, V transpose, and I multiply with V sigma squared V transpose. So I'll end up with V sigma to the power 6 times V transpose. Okay, so there's some nice pattern here, right? So in summary, what is y to the t? If I raise this matrix to the tth power, what do I get?
V times sigma to the 2t times V transpose.
Exactly. So there's something nice here, that the v is not changing, but sigma is kind of becoming, is just being raised to a higher and higher power. Okay. Now, when I raise these numbers to higher and higher powers, what can happen? So, also keep in mind that we know y. We don't know what v sigma and v and sigma are, but we know y is just x transpose x. X was our input, and our goal was to compute the first singular vector of x. So I can always compute x transpose x. I can always compute y to the t by just matrix multiplication. But something nice is happening here, and as I exactly pointed out with Direct, the largest entry is getting a lot larger than the other entries in particular. So let's suppose for some reason, let's say the largest entry, we normalized it so that that was 1. I'm trying to understand how the sigma scale with respect to each other. And sigma 2 is a half. Okay, maybe half also seems a bit too optimistic. Let's say it's 0.9. Okay. So the 1 and 0.9 are not important, but you should think of I'm saying sigma 2 is 90% of sigma 1. Once I go to singular value, there's a drop of 10%. Now, what happens when I raise these things to the higher power is I get V, and the first one stays 1, but everything else is becoming small at an exponential rate. So this is something like, this is less than or equal to. So I can write this as summation I equals 1. So let me write it as sigma 1 to the tt times v1 transpose plus so the vi's are staying the same, but the sigmas are being raised to higher and higher powers. So if this is 0.9, then 0.9 raised to the 100 is a very, 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 very small number, right? So as p increases, what is this whole matrix looking like? What is it going towards?
Sigma 1 to the 2t v1 transpose.
And sigma 1 to the 2t we said is 1, right? So it's basically like v1 transpose plus some things which are decaying at an exponential rate. An exponential rate is amazing. If I do it 10 times or 100 times, then you should really only see v1 transpose as t goes to infinity. Okay, because all of these are 0.9 to the 100. right, which is a very small number. Okay. So I don't know v1, but I can compute y to the t for large enough t, right? Let's say I do t equals 100 or t equals 500 even. I get some big matrix now. How can I extract the first singular vector from that? If it is v1 transpose, how can I compute the singular vector, first singular vector? So here, what is the first column of v1 transpose? Well, it's a square matrix, right? So this is v1 times v11, right? So the first column of v1 transpose is just a scaling of v1, right? So how can I extract the first singular vector now if I can compute y to the t for a large enough t?
Just normalize it.
Exactly, right? So here's the idea then. Step 1, compute y to the t for a large t. So think of it as like 100 maybe. 2, compute first column, output first column of y to the t divided by norm of first column. Okay, I'm just normalizing the first column, and if this approximation is very good, then presumably what I'm getting out should be close to the first right singular vector, v1. Okay? Make sense? Alright, so let me break it up into one more step just to make things a little more evident. Compute, let's say, v prime is first column of y transpose, y to the t, and output v prime divided by the normal. Okay, so this is a 3-step sort of heuristically reasonable algorithm. We haven't analyzed it, but it's simple enough. But this is almost like using a sledgehammer to kill a rat, right? Because I wanted a singular vector, but I'm multiplying y 100 times. And matrix product is a very expensive operation. If I had to multiply a 500k matrix, 500k times 17k matrix with itself and so on is going to be super expensive. Because we say even storing the matrix is like 8 GB size matrix. How do I multiply two matrices of size 8 GB? I can't even fit them in my RAM that easily, right? So what's the go around for that? Do I really need to compute y to the t here? Do I need to compute y to the 100? What do I want? I only want the first column of y to the 100. I don't want the entire matrix y to the 100. I only want the first column. Is there a way to compute just the first column without having to compute the entire matrix? What do you think? So let me write it slightly differently. The first column of any matrix is, let's say this is y to the t. I can write it as a matrix vector product. What should the matrix vector, what should this vector be here? If you want to extract the first column of a matrix as a matrix vector product, if I just put 1, 0, 0, 0, what do I get? I just get back the first column. Okay. So now what can you tell me? To compute y to the t times this vector, do I need to compute y to the 100 and store that matrix, or can I do something cleverer? Okay, so this is what v1 prime is. And what we wrote down here is, okay, I want to compute this guy, so I'm computing this matrix product and then multiplying with this vector. But what's a more efficient way or better way to do this?
Start from the right.
Start from the right. Because you never have to multiply matrices if you start from the right. So what I'm going to do is to compute things like this. Okay, and that's basically the power iteration. Right? So idea is, for L equals 1 to t, you start with, let's say maybe v prime 0 is the vector 1, all zeros, and compute v prime L is y times v prime L minus 1. Okay, so this is a much faster algorithm, not computing matrix product ever, which is a super expensive operation. All I'm doing is a matrix vector product, which is much easier computationally. Although there is one catch, right? So what was y? Y was x transpose x. Do I even have to compute y for this algorithm? No, I can use the same trick again, right? That's it. So that's the power iteration algorithm. Okay, so let me move this up. Okay, so this is the power iteration algorithm, more or less. The only thing is we'll do something, we'll change it slightly in the next lecture to make it a bit more robust. Okay, the algorithm is kind of based on this simple intuition. It's again a simple two-step update where I'm just multiplying a vector with the matrix again and again. And the only change we'll do to this for numerical stability reasons is instead of normalizing at the very end, we're going to normalize each time. Because if I keep multiplying a vector again and again, and then I try to normalize at the end, maybe in between the numbers become like really big, like 2 to the 100, 2 to the 200 or something. And then I divide by 2 to the 200, that's like a really meaningless thing to do. when you think of implementing things on a computer. So what you do is just multiply, normalize, and so on. It's the same thing and slightly modified, and that's exactly the power iteration algorithm. And we'll show in the next lecture how we'll understand how it will perform when we apply it to compute the first singular vector. Okay? So this is our approach for computing the first singular vector, and we'll study it in more depth in the next lecture. Okay? That's all for today, and remember that assignment 3 will be out today and is due a week from now, next Monday at 10 p.m. as usual. Bye everybody.